Hello everyone, today I am going to introduce our latest work, Knowledge to Size, Reasoning over Visual Attribute while Knowledge Decomposition for Abnormality Grounding. Visual grounding is a really important task, which the user gives the target they want to locate in the text format and the model generates the bounding box. There are two ways to do that. The first is based on DIRT and fast Arch-Endian architecture to generate the bounding box first and compare the similarity between the text input. The second way is use the large vision language model directly do the grounding task. The user directly gives the text to the large vision language model, and the model generates the bounding box in text format. In the technical report of Q1 2.5 VR, we can find that their performance already outperformed the grounding dyno. Medical abnormality grounding is fundamentally different. Here, the model must localize subtle pathologic findings. These abnormalities often show more subtle change than simple visual recognition tasks. As shown on our experiments, performance drops dramatically when general models are evaluated on medical image. This also demonstrated on other papers with brain MRI, which highlight the large perception gap between general domain grounding and the clinical grounding. Based on the experiment, the general VLN falls on medical perception tasks. Specialist VLNs are more accurate, but they are also trained with huge amount of datasets, which are costly. So we aim for the best of both worlds, specialist level grounding with compared general purpose VLNs guided by smarter supervision instead of massive data scaling. We want to teach the general purpose model learn what they are look for and learn the tasks more effectively. Our motivation is to bridge clinical language and visual perception. Clinicians describe abnormalities through visual attributes such as shape, location, and density, rather than single disease labels. And as shown on the right, based on our methods, a compact 0.23 billion model achieved comparable performance to a 7 billion parameter specialist model. Here is an overview of our method. Our framework consists of two main stages. First, the knowledge decomposition constructor, and the second is semantic guided training. Now I will explain our method in two parts. First is the knowledge decomposition constructor, which turns in medical terms into visual grounded with supervision. In the first stage, we start from medical terms, for example, lung opacity, and retrieval is clinical definition from medical guidelines. These definitions are usually long and contains many concepts that are not directly related to the visual clues. So we distill this definition into visual attribute using the GPT-4o with a visual distinct instruction. Based on this process, we obtain a collection of visually oriented descriptions that combine attributes such as shape, intensity, and location. Finally, we perform human evaluation to select the most consistent and the clinical meaningful attribute description and convert them into a final grounding instruction. In the second part, we use this grounding instruction for semantic guided training. Given an X-ray together with the visual definition instruction, the VLN learns to generate abnormality description along with the bounding box coordinates. We train the model using cross-entropy supervision, so it's learned to align clinical concept with visual regions. In this way, the model learns both what the abnormality is and where it's located. We evaluate K2Sight on two datasets. First is the WinDR-CXR dataset, contains 22 abnormalities with over 16,000 training samples. And another dataset is PET-CHESS-GR, evaluate generalization ability and includes both known abnormalities and unseen out-of-distribution diseases. This allows us to test not only performance but also robustness to unseen diseases. Here, we show quantitative examples through our demo interface. Given clinical description, K2Sight generates grounding abnormality localization on chest X-ray. Now, we evaluate how effective K2Sight is compared with existing approach. Across both datasets, K2Sight show more and comparatively performant compared to the large specialist VLNs. Importantly, it used less parameter of the model size. This showed that intelligent supervision can compensate for model size. Next, we studied whether K2Sight can fit compact general-purpose VLNs towards specialist-level performance. When removing the knowledge decomposition model, performance drops consistently across datasets at the backbones, including the more challenged PET-CHESS GR. This confirms that knowledge composition is crucial for both performance and the generalizations to known and unknown diseases. We further analyzed the contribution of individual attributes. All attributes contribute to grounding performance. Location and shape have stronger influence, while intensity contribution relatively less. Interestingly, the light model shows higher sensitivity to attribute removal, indicates stronger reliance on structural supervision. To conclude, first, small models can outperform large specialist models when guided with structured knowledge. Second, intelligent supervision is more effective than brute force data scaling. And finally, teaching AI to precise medical image the way clinicians do enables strong generalization even to unseen diseases. Future of AI not bigger but smarter. Thank you for your listening.